I have some hot tea right here, and I just measured its temperature, and it's 80 degrees Celsius. But I want to know how this temperature is going to change over time. Luckily, I have Newton's law of cooling. It reads as follows. The change in temperature over the change in time is equal to negative K times the temperature minus the temperature of the environment. So this may sound like nonsense, but what it's saying is actually pretty simple. So the rate of change of the temperature depends on two things. This constant K, which just depends on the object you're using. So like things with different surface areas or different compositions would have different K, but for a given object, K should stay the same, so we can just solve for it. The other thing it depends on is this T minus Tn term. What that's saying is the closer the item is to room temperature, the less the temperature is going to change over time. So something with like a wildly different temperature would have this term be very high, so the change in temperature over change in time would be high. But if these two are like close together, this term's going to be about zero, so the temperature is barely going to change. And that, intuitively makes sense. Okay, but how can we actually use this formula? There's some calculus involved that you shouldn't worry about, but there's a way to rearrange this to have just temperature of a given time. And that can be evaluated as the temperature of the environment plus some constant C times e to the negative kt. As you can see, it is a function of exponential decay. And if you look over here, you can see that as t grows to infinity, this e to the negative kt term will grow to e to the negative infinity, which is 0. And so after enough time, the temperature of the object will be the temperature of the environment. So, it kind of makes sense as a formula. But, now we have these two constants, C and K, that we need to solve for. K is the same as before, and C corresponds to the original change in temperature the original difference in temperature between the object and the room. So if you plug in time equals 0, we have that the T of 0 is environment temperature plus C times e to the 0. And, we have the data point for time at 0. It's 80 degrees Celsius. So we have 80 equals 22 room temperature plus C. And we can solve for C equals 58. Now, it's been about 150 seconds, so we can measure the temperature of this hot tea again. And it's 70 degrees Celsius. So how can we use this new data point? Well, we can use it to solve for K. So right now we have that the temperature of 150 seconds is 22 plus 58, 58 comes from C, of course, times e to the negative k times 150. 150 is time. And how do we use this to solve for k? So first we can subtract 22 from both sides and divide by 58. So we have 70 minus 22 divided by 58 is 48 over 58 is equal to this e to the negative k times 150. Now we can take the natural log of both sides and then divide by 150, and now we have a value for our k. So hopefully you can follow how I did that. And now we can just plug this k into our formula, and we have an accurate formula for t. So for example, if we wanted to know the temperature after 200 seconds, we could just plug it in like that and put it into our calculator, and wow, it's about 67 degrees Celsius. Now let's talk about when this formula won't actually be useful to us. So in the form we used it, the math relies on the fact that the C and the K will stay constant. However, this won't always be the case. For example, an ice cube melting might have very different properties at different stages in the process. At the beginning, it is a relatively dry cube of solid ice touching only the air. However, after a couple of minutes, there might be a puddle of water covering part of the bottom of the ice cube, and its surface area might have shrunk where the corners of the cube smoothed out. Even accounting for this, measuring the temperature of the partially melted ice cube would be misleading. You would always measure a number below 0 because you are not accounting for the already melted water. In a more complex system like this, it's much more difficult to effectively use the formula. It works best for objects that keep a constant shape and composition, have uniform temperature, and which remain in an unchanging environment. Thank you.